Today I'll be demonstrating one method on how to determine the polarization in a piezoelectric material. So before we do that, I'm just going to briefly review essentially what polarization is and how it's created. So as you may remember, a piezoelectric material initially has a lot of different polarization inside of it, and so a lot of different dipole directions when you first make it. But then what we do in the factory or in your lab, you apply a very large voltage, you apply large voltage to the piezoelectric material. This says large, L-A-R-G-E, and then because of that, the polarization, more or less, they get aligned. See, the net polarization, because all the polarization vectors are going all of these different ways, they all cancel each other out. But in this case, after you pull it, by aligning them, by using a large electric field, we get a polarization. So what exactly happens here? So if we get, positive charge, appearing because of the applied field, and then we get negative charges at the top. And so negative, so let me just draw it like that. We get negative charges appearing at the top, and we get positive charges appearing at the bottom. So, opposite to my drawing, the internal field developed due to the remnant polarization, or the spontaneous polarization which is created, is going down toward the positive. So dipoles moment, and similar to the same as polarization, is opposite to electric field, where the dipole moment goes from negative to positive. And this is similar to the applied field. So this is the applied electric field, that's E, and then the resulting spontaneous polarization is also down. So this is kind of a good convention that the spontaneous polarization is going to be in the same direction as the electric field, and that's going to be down for this material. Now if we continue to describe that, when we have a piezoelectric material and it has a certain polarization, and remember the polarizations end on positive charges, and the negative, and the tails is negative. It's opposite to electric field. And if we push on it, we are going to get these positive charges will be going down, and these negative charges will be going up. So the positive charge, so positive will start to develop here. This is a simple way of thinking about it. Negative will end up developing here. So which direction is the electric field? The electric field goes from positive to negative, and so does voltage. So this will be the positive voltage, and this will be the negative voltage, or ground, you could say, if you want it, if you're attaching everything to ground. So this will be the positive voltage and the negative voltage. If you had your polarization going the opposite way, and you squeezed it, and you squeeze this material, you would have the opposite happening. The positive voltage will end up happening at the top, and the negative voltage will end up happening at the bottom. So the typical convention when they manufacture piezoelectric materials is that when they pull a material, meaning that they apply a large field over here and a negative field over here, or ground rather, and then the polarization orients itself like this, they put a dot at the top of the material. And you may find that in your piezoelectric materials you have in your lab or whatever you're using, there's a dot, and that dot represents this positive voltage which is applied. And basically it's the tail of the polarization. The positive voltage is the tail of the polarization. And similarly to this figure, if the dot, see, in this material the dot will be at the top, and this material the dot will be at the bottom. So basically, if you squeeze a piezoelectric material and you end up with positive voltage at the top, this is positive, then you should put the dot at the top. And if you squeeze the material and you end up with negative voltage at the top, you put the dot on the bottom. So you put the dot wherever you would find the positive voltage. And I'm going to explain this, and we're going to actually do it using a piezoelectric material and an oscilloscope. So we have this oscilloscope, and what's essentially going to happen, if we can get this on correctly, and looking toward here, we have our oscilloscope. We have a voltage probe here, and we have like a metal piece, you know, something metal right here. So basically what we will do now, and we have this piezoelectric material. You see it's shiny on one side, shiny on the other side. Those are metal electrodes. In the middle there's a ceramic material known as PZT. It's and this is a poled piezoelectric material, so it has a polarization, a net polarization which you can measure. So let's find out what it is. So I'm just going to simply put it on here. I'm going to show you the test setup, and then you're not going to see it anymore. And then we just basically put this in here. I'm going to touch this. See that happening on the oscilloscope? You're going to have your that's not what I'm actually going to do, but anyways, you're seeing some of that effect. So I'm going to touch that, and when I'm touching it, I'm going to hit it with this pen. I'm going to hit the piezoelectric like this on the top. While I'm touching it, I'm going to hit it like that. So I'm not going to show you that, just so you can have a clear view of the oscilloscope. So I have the piezoelectric material. I put the ground plug on. I'm touching it with the voltage probe. And you're sort of seeing my hand hit this thing. And you see you got to watch out for the trigger here, because you know if we squeeze the material, and the dot should go on the top, then the material is going to jump up positive voltage. So here we hit it, positive voltage happens first, and negative voltage happens second, because piezoelectric materials are springs. So you compress them and you let them go, they're going to overshoot, and they're going to come back down, and you know they're actually little springs. You know, all materials are sort of like springs. So you don't normally get to see this effect, except that this is very sensitive because we're using voltage sensing. A piezoelectric material is a sensor in itself, and this makes it really easy to measure its different properties, because it itself can be used as a sensor to measure itself. So there we go. We have positive voltage happening first, negative voltage happening second as the piezoelectric material expands again. And we have here negative voltage happening first. I'll just give you a little look of what I'm doing here. So this can be kind of confusing about which side, because you gotta really see that. So when you hit it, you should leave it down, just so you keep it going one side, so it's easy to see. That's negative. That's negative. So the polarization vector ends here. So the nose of the arrow of the polarization vector ends on this side, and it starts on this side because it's positive. And as I just explained, you can review the last couple of minutes. Since we have a couple more minutes, you can either stop now. Now what we'd basically do, you'd hit it. You find it was doing positive, something positive like this. You'd say, hey, this is the top. You take your marker or whatever you have. If you just want to confirm it, you just mark on the top like that. Just mark. There you go. Now you found your polarization vector, and from that you can tell if you want to orient your electric field in the same direction as the polarization vector, which is pointing now downward. If you orient your electric field with positive charge voltage here, negative voltage here, the piezoelectric material is going to expand in its thickness. If you plot in positive voltage here and negative voltage here, it's going to contract in its thickness. And remember, if it contracts in the thickness, it's expanding in the width, and if it contracts in the width, it's expanding in the thickness. So this is known as the 3-1 effect or the 3-3 effect, and you can listen all about that in some other lectures which I've done or I'm going to do. So basically we just determine the polarization direction. It's going down, and because we hit it, positive voltage came, Positive voltage means the dot should be on the top. The dot on top means that this goes down. The polarization vector goes down. Now I'll try to capture it. Now you can stop watching now if you want to. This is all you need to know. But I'm just going to try to capture a good glimpse. So I'm going to press single sequence. And the problem with single sequence is it keeps capturing data I don't want. So I'm going to hook this up again. I'm going to increase the level, and I want to get only a single sequence here. I'm going to do an auto set, and I'm going to increase the scale to 1 volt and decrease the scale to 40 milliseconds per division and 1 volt per division on the way up. I want to do single sequence, which is not the best way to do it. I can't get it to work out. I forgot how to do that. So we're going to increase the level here again. And you want to reject that HF noise. There we go. Just like I said, it's positive, right? Try it again. There we go. So we just saw this position. Let's just bring it back here. Single sequence again. That's it. See how it, like, when I'm hitting it, this is actually what's happening in the materials. Now going to, if you increase the scale, I can show you a little more. You can see that it has these effects, and it's important also, you know, this material is going to have some, let's just run it. I'm doing continuous run again. It may have some charge left on it, so you could just take like sort of just kill the charges with something, connect some wires, or it may have some charges build up. That's probably not going to be the case. Not really the case here. The voltage developed was much more, and so basically you can hit it. You may need to change, like I said, the trigger is an important thing to consider. The slope, whether the voltage is going down, it's going to trigger when it's going down, so you should be careful. But I think I just showed, and we'll do it again to make it even more clear to you. Increase this single sequence up. You scale, look, it went up first. See, the voltage went up first before it went down. So, this means it's dots on the top, voltage is going down. Sorry for the redundancy, but this stuff is very important for anyone to know. Next video, I'm going to show how to determine the polarization using a different method if you don't want to use an oscilloscope. Thanks for watching.